Today we're talking about clustering and association rules mining. We will see the basic concepts about creating clusters from data, which is an unsupervised learning method where the machine learns by examining the values of the attributes and the distance between the objects and placing them in groups of similar objects or items. Association rule mining is a separate subject in which we are extracting rules from the data that are in the form of an if-then statements. For example, if we buy pizza, we also buy Coca-Cola 90% of the time, unless we buy Pepsi, which is the other 10% of the time. These are called associations. That this kind of rules can be extracted from data, usually transactional data, to find relationships or correlations between the items that are being purchased or that are in the same transaction together. The most popular algorithm for this is called Apriori algorithm. We will look at data formats and the way the data is stored and organized before we start extracting these kind of patterns such as clusters and associations from the data. So we will discuss certain post-processing tools such as support and confidence that can be used to sift or filter through the accomplished results in order to present the user with the most interesting, useful and actionable knowledge that is discovered from the data. So let's start with clustering. We mentioned that with clustering we will find the distance between the objects in the data, and the objects that are close to each other we will place them in the same group. So we are creating groups of objects. The reason they are similar is because they're close to each other. So similar objects are close to each other on a visualization or a scatter plot where each item is plotted as a dot on the coordinate system, as we have seen in the previous 2 or 3 lectures. If we have the coordinate system x and y, two-dimensional space, the values of each object or item on those coordinates is taken from the data, the object is plotted into the two-dimensional space, and each object appears as a dot onto our visualization. The dots that are close to each other we place in the same group because the values of their attributes are similar. That's why they're close to each other on the picture. Therefore, we would compute distance. We can use any distance measure, such as Euclidean distance, Manhattan distance, or cosine distance, any distance measure that we believe is appropriate for the current data we can use. And then the items that are close or closest to each other would be placed into the same group. This kind of analysis can be used in real life for applied in a variety of scenarios. For example, demographic analysis, maps, that is maps of geographical maps, probability densities, and conceptual clustering. Let's see how the clusters are computed and visualized. As we mentioned, in order to compute the similarity or the distance, we can use a measure. Measure could be something like Euclidean distance distance cosine similarity. This is just to name a few, but there is a variety of distance measures that can be used depending on what the data is. If it is a binary data, then we can no longer use Euclidean distance because we only have zeros and ones. So for that reason, we need to use something like a Jaccard coefficients. Or whatever the data is, we need to decide the most appropriate measure for that data. Okay. So, given the set of data points, each has a set of attributes, and the similarity measure that we will be using, it can be one of those in the pink color here. Find the clusters so that the data points in one cluster are similar to each other and the data points in the separate cluster are far away from each other. So the points within the same cluster should be close to each other, and the points in the other clusters should be away from each other. So we are maximizing the distance between the clusters themselves and minimizing the distance between the items within the same cluster. Okay, Euclidean distance, this is the intuitive everyday distance that we would measure by taking a ruler and measuring, let's say, 5 inches or 12 inches or 3 feet or 10 feet or 25 miles between the cities. This is the everyday distance that we use. It's called Euclidean distance. There are other distances, as we mentioned, depending on what the data is, because if the data is binary, this doesn't make any sense, to be computing 25 miles between the cities, because the data is just zeros and ones. So we have to choose the most appropriate measure for our purpose. Let's see here how the clusters look like. We have mentioned earlier that we have two axes, the x and y, when we have the two-dimensional space. When we have the two-dimensional space, they're going to be two axes, x and y. In three-dimensional space, we would have three axes. In three-dimensional space, we have x, y, and z axis. So what we are seeing here is three-dimensional space. The x is over here. Y is over here, as we have seen so far. So let's say this point right here this point right here, is having certain value for x and certain value for y from our data, and that is why the point is located in this location on the visualization. Now, if we also take the z-axis, it will have three values that determine its location, and the z-axis will give us the depth or the three-dimensional space. And that is fine. It can have three axes. That means it has three attributes in the data table, or three values that we are using to plot the items as well as to compute the distance. So we would like to create clusters that are items within the clusters are close to each other. So this would be the cluster 1 here, because there is a bunch of red dots that are close to each other in a similar location onto the picture. Then the yellow dots would be cluster 2. And the green ones, cluster 3. The idea is the items within the same cluster are close to each other. Items, the distance between the red cluster to the yellow cluster should be as big as possible. The distance from the red cluster to the green cluster should be as big as possible. This allows us to create well-separated clusters. Now, this is the case with divisive methods such as k-means, clustering, so divisive methods such as k-means creates well-separated clusters. That is, the distance between maximize distance between clusters and minimize distance items within same cluster. That is what we would like to accomplish with this particular clustering method. As we mentioned, this kind of finding of groups of similar items has many applications. We could group similar documents together. For example, all the web pages on the web, on the World Wide Web. If we want to, we could group them as groups of similar documents or pages. So all the web pages that talk about pizza, food, and cooking and culinary arts would be grouped into the same cluster. All the pages that talk about recreational vehicles and traveling in nature, climbing mountains or trails would be grouped into another cluster. And all the web pages that talk about computer science and computer programming and data visualization would be grouped into a third cluster. So we could create groups of similar documents like this. Another idea is if we have, for example, business data, we could group similar markets together into the same cluster, or we could group, let's say, profitable customers into group 1 and non-profitable or high-risk customers into group 2 or cluster 2. We could group patients or medical data, patients that are, for example, healthy and of young age and of a particular location, could be grouped together versus the patients that are older and have specific disease or are at higher risk of a heart disease or a cancer or some other medical condition, would be grouped into another group. So in that situation, we could use geographical or lifestyle related information. Really, the information that we use does not make any difference. The clustering algorithm is going to follow the same method to discover the groups of similar objects, no matter if they are medical records and patients, no matter if they're business data, or if they are meteorological data. It's still going to find the groups of items because the only thing that it is doing is computing the distance between the objects based on the values x, y, and z. So it is just doing some simple math to find the distance according to the attribute values, and it has no knowledge and no idea of the meaning or the semantics of the data. So whether this is medical data, educational data, or financial data, it's still going to find the clusters of the similar items. So whether these are the web pages on the World Wide Web that is trying to group together. So that is what the clustering does. Now we move into the subject of association rules. So association rules is a different data analysis tool than the clustering. It allows us to find associations or correlations between the attribute values and how one affects another. So, for example, if we have transactional data, let's say we go to the grocery store and we purchase a bunch of items together. Let's say we purchase bread, milk, and fruits and place them into our shopping cart or shopping basket. We can, by recording a bunch of those transactions, let's say we are the retail store, the grocery store, today they came in 100 customers, each one placed certain things into their basket or shopping cart. Once we have recorded these 100 transactions into our database, we can go on to analyze those transactions to determine which of those items are frequently purchased together. Let's say if the customers purchase bread, then the arrow here means then. So this is basically a if and then statement. So let's just clarify this. These are, the rule is an if then statement. In other words, if we have bread, then we have milk. And certain measures can be computed here, such as support and confidence, to tell how confident we are that this is the case. If we have, so let's say today 100 customers came, we recorded 100 transactions. How many of those purchased bread, first of all? 5%. How many of them purchased the bread and the milk together? 5%. How many of them, when they purchase bread, they also purchase fruits? 4%. So, we could calculate this kind of measures just to tell us how confident they are and in how many of the transactions this happened. So, support, what you see here, is bread and milk occurring together how many times into our 100 transactions that we recorded. This support 5 shows out of 100, 5 of them contain bread and milk. Confidence 100% because every time we bought the bread, they also bought milk. Now, if there were one time one person bought bread and didn't buy milk, the confidence would be a different number other than 100. So let's say somebody came, bought bread and fruits. Out of the 5 transactions, 4 of them have bread and milk, and 1 of them has bread and fruit. Then support will still be 5, but the confidence would be 4/5. So how much is that? Instead of 100%, it's gonna be 80%. So the confidence, it's going to take the number of times the items occurred on the left side of the rule and divide it by the number of times both items, left and right, occur into the data. So here we have confidence 100%. This basically means every single time there was bread, the milk was also purchased. Okay, so let's see. In this way, we can find dependencies or correlations in between the items. This can be used as an actionable knowledge by the retail store because they could figure out that people oftentimes buy bread and milk together and they can take some action based on that in order to improve their profits or to accomplish their goals. For example, they could rearrange the store layout to place the bread and the milk in the same place because they're usually purchased together. This way, when a person comes in and buys bread and they see the milk right next to it, they'll be like, oh, I should also get milk. And this way, they end up buying more things, sometimes buying more things than what they intended, so that the retail store maximizes its profits and sometimes just making their life easier so they don't have to walk around the store to figure out where the milk is, but it is right there, right next to the bread, because that helps to find the items that are usually purchased together. This could be working for services as well. Let's say a phone company is offering certain services, voicemail, caller ID, call forwarding. How often people that buy voicemail and caller ID would also buy call forwarding? And they can decide which of its services to place on promotion, because let's say most of the people that buy caller ID also buy call forwarding, well, then the ones that bought caller ID, we're going to offer them now call forwarding because we're pretty confident 100% or 90% that they are actually going to buy that service. This is also used in large e-commerce websites such as Amazon. Let's say we go and buy on Amazon, we buy diapers. We go to Amazon and we buy diapers. The Amazon has collected the data of all the people's Amazon.com that is buying diapers, and what other things did they place into their shopping basket? Well, most of the time when they bought diapers, they also bought beer. Weird enough, but that is what the data is showing. So, if that is the case, remember, we don't care about the meaning of the data. If it is beers or beer and diapers, if it is pizza and Coca-Cola, if it is bread and milk, or if it is call forwarding and caller ID, or if it is what's causing cancer and heart disease, we don't care. The algorithm doesn't care. It has no knowledge about the meaning of the data, the semantics of the data, the domain of the data. It just does its calculation. It looks at the transactions. If there were diapers and beers, guess what? We're going to create a rule that says if people buy diapers, then they also buy beer, because that's what our data is showing. Showing this support 5% of all transactions contain this stuff, and confidence is 60%. So we can, Amazon, by having this in its database, and somebody came in and clicked about to buy the diapers, the Amazon will say right under the shopping cart, by the way, you might also be interested in beer and in all these other products, because most customers that buy diapers also buy these other things. So we suggest you to look at them, and usually those are pretty meaningful. Just think about when you have been to Amazon.com and you want to purchase something. Right underneath, it starts giving the suggestions of similar items or items that have been purchased together along with what we just placed into our shopping cart. So it will suggest similar items. Or it will suggest items other people bought. Okay, so this has quite a bit of practical applications that is used as well as in physical retail stores, as well as in online e-commerce stores. And as we mentioned, it can be applied to any kind of data, whether this is manufacturing data, medical data, educational data, and even government data. So here's another example. 98% of people who purchase tires also get automotive services done. So let's see see real quick how do we extract this kind of rules from the data. This is a transactional data right here. Transaction ID 1, 2, 3, 4, 5. The items that were purchased together: ABC, AC, AD, BEF. This ABC will represent bread, milk, and fruits, or diapers and beer, or whatever else we would normally purchasing into that retail store. So what we would like to do, first of all, the way this algorithm works is it takes it looks for frequent item sets, and by frequent we mean that have a support higher than what a particular threshold is, let's say 50%. Any sets or item sets that have support higher than 50% or 5 are considered frequent. So we're going to first scan our database, start with single item sets like A, B, C by themselves, and count how many times this item occurred in my database. The item A over here occurred 1, 2, 3 times. The item B occurred 2 times. So 3 times out of 4. We have only 4 transactions here. Only 4 rows. 3 of them contain A. So 1, 2, 3 out of 4, that's 75%. So that's what we have for A. Now B, on the other hand, only occurred 2 times. 1, 2 out of 4, that's 50%. The same situation for C. Well, all of these are fine because the minimum support we look for is 50%. Now, if some of them had a 25%, like the item F only happened 1 time, guess what? It doesn't meet the minimum support threshold. Therefore, it is not listed in as a frequent set. The F is not a frequent set, and we're not going to list it into our frequent set table. So, out of the ones that are frequent, what we're going to do is start creating 2-element sets. So we started with a single element like A, B, and C on its own. A by itself, B by itself, C by itself. Now, from the frequent sets, we will combine them together to create 2-element sets. For example, A and B together, A and C together, B and C together, by taking all the possible combinations between A, B, and C, which will be AB, AC, and BC. So all of these are going to be recorded here, starting with AC. And now the same thing. We're going to check how many times A and C happened together in our database. So A and C 1 time, A and C 2 times. 2 times out of 4, that's 50%. And therefore, A and C is a frequent set. How about A and B? How many times that one happened? Well, only 1 time, right here, AB. So that's 1 time out of 4, that's 25%. That doesn't meet our minimum threshold. Therefore, it is not listed into the frequent set item set table. The same situation for B and C together. How many times B and C occurred together? 1 time. 1 out of 4, that's 25%. That's less than the minimum support threshold of 50%. Therefore, it is not listed in the frequent item set table. So, once we're done with finding the 2-element frequent sets, we'll go to 3-element and 4-element. And with every increase into the number of elements, we will get less and less frequent sets. In this case, there is only 1 2-element frequent set. That is why we stop, because we can no longer combine them together since we only have one of them. If B and C was listed here, we go to a 3-element set such as A, B, C. Now, how many times A, B, and C, the three of them, happen together? It's only one time. But that would be listed here if it was more than that, to where it was bigger than the minimum threshold. Okay, so what do we do now? We take those frequent sets that we discovered and we create a rule from them. So the rule here, it's going to say from AC, we get a rule that says A implies C, and that is the case. Support 50%, and confidence is what? The confidence is the support divided by the left side of the rule. Oh, wait a minute. The support is not 50%. Support is 25% because A and C. Oh no. A and C we have them 2 times. A and C here and A and C here. So out of 4 transactions, 2 times is 50%. Now the question is, what is the confidence for this rule? If we have A, how many times we also have C? Well, A happened 3 times, while A and C happened 2 times. So it will be 2 over 3. So it will be 2 over 3, or 66%. So, out of the AC set, we can extract this kind of rule. We only have one set here, A and C, so that would be the only rule, but if we had more, we would extract the rules from them as well. Okay, so that is in essence how the association action rules are extracted using the a priori algorithm.